Humanity has, in total, brought back a little under 383 kilograms of the Moon. 6 Apollo missions, 3 Soviet lunar missions, and China's Chang'e 5. 11 successful sample returns across half a century. Every single one of them came from the near side. Every rock in every laboratory on Earth, every measurement in every textbook, every model of how the Moon formed and cooled and died, all of it was built from material collected on one face of a two-faced world. And the two faces are not the same. Look up at a full moon and you see dark patches, broad, smooth, gray-black plains, ancient oceans of frozen lava that flooded across the surface billions of years ago and then hardened in place. Turn the Moon around and they are almost gone. The far side is a different world. The crust is thicker. The chemistry is different. The magmatic history is different. Where the near side is scarred with vast dark seas, the far side is pale, cratered, and comparatively quiet, as though volcanism simply chose one hemisphere and ignored the other. Scientists call this the lunar dichotomy, and for decades, nobody could explain it. There were ideas. Perhaps the great ocean of magma that once covered the young Moon crystallized unevenly, faster on one side than the other. Perhaps tidal heating from the Earth warmed one hemisphere more than its opposite. Perhaps a very large impact on one side or the other rewrote everything that came after. All of these were hypotheses, reasonable ones. But you cannot settle an argument about rock without rock, which is why the landing site was chosen with such precision. On the far side of the Moon, in the southern hemisphere, there is a wound. It is called the South Pole Aitken Basin, and it is the largest confirmed impact basin in the entire solar system. It measures roughly 2,500 kilometers across. It is the deepest structure on the Moon, and it is the oldest, formed somewhere between 4.2 and 4.3 billion years ago, in the earliest era of lunar history, when the solar system was still violent and unfinished. Whatever hit the Moon to make that basin did not just scratch the surface. Gravity measurements show that the crust beneath parts of it is among the thinnest anywhere on the Moon. Modeling suggests the impact excavated material from between 80 and 120 kilometers down, reaching through the lower crust and, quite possibly, into the mantle itself. Inside that basin sits another one, the Apollo Basin, a peak ring structure about 490 kilometers wide, the deepest and largest impact scar contained within South Pole Aitken. And inside that, on a flat plain of dark basalt lying between the inner ring and the southern rim, is where Chang'e 6 came down, roughly 41.5 degrees south, 154 degrees west. The terrain around it is dotted with wrinkle ridges and with Kipuka's islands of older, higher ground that the lava flowed around rather than over. The lander itself settled on the flat edge of a small impact crater, about 50 meters wide and 3 meters deep. The basalt underfoot has been dated, from crater statistics, to somewhere between 2.79 and 2.87 billion years old. So the scientific hope was very specific. If the original impact really did punch down into the deep interior, then some of that deep material might still be lying in the basin. Scoop up the surface here, and you might, by accident, be scooping up the inside of the Moon. Chang'e 6 launched on the 3rd of May, 2024, at 27 minutes past 9 in the morning. Coordinated Universal Time, on a Long March 5 rocket from the Wenchang launch site on Hainan Island. It was the 6th robotic lunar mission flown by the China National Space Administration, named like every spacecraft in the program before it after the goddess of the Moon in Chinese mythology. The whole stack weighed about 8,200 kilograms. The lander alone accounted for 3,200. The little ascent vehicle that would eventually carry the samples off the surface weighed around 700. 5 days later, it slipped into a 12-hour orbit around the Moon. Now, here is the first problem, and it is a fundamental one. You cannot talk to a spacecraft on the far side of the Moon. Radio does not bend around 3,500 kilometers of rock. Every command, every telemetry packet, every fragment of data has to go somewhere else first. That somewhere else was Queqiao, a relay satellite already positioned to see both the far side and the Earth at the same time. Without it, Chang'e 6 would have been deaf and mute the moment it crossed the horizon. On the 30th of May, the lander and ascender separated from the orbiter. 2 days later, from an altitude of 200 kilometers, the descent began. The spacecraft came down using an autonomous obstacle avoidance system, a visible light camera, and a laser three-dimensional scanner reading the ground beneath itself in real time, picking out boulders and slopes, steering around them without anyone on Earth in the loop. There was no time for a human to intervene. There was no signal path for a human to intervene through. 17 minutes after it started, it was down. Then the collecting began. A robotic scoop for the surface, a drill for what lay beneath, reaching about 2 meters down. The scooping was done in 8 separate passes at a single location, each one going no deeper than 3 centimeters, yielding around 1,610 grams on its own. And when the drill withdrew, the hole it left behind in the lunar soil happened to form the shape of the character Zhong, the first character in the Chinese name for China. Nobody planned that. Images of it spread across Chinese social media within days. There was one more passenger. Riding on the lander was a mini rover weighing about 5 kilograms, wrapped in gold insulating sheeting, which earned it the name Jinchan Golden Toad. It carried its own micro-solar panels and an infrared spectrometer for studying surface composition and looking for water ice in the soil. It also had a much simpler task. After the sampling finished, the little rover detached itself, drove to a suitable spot, selected an angle, and photographed the lander sitting on the far side of the moon. It did all of that on its own. At 38 minutes past 11 at night, on the 3rd of June, the ascent vehicle lit its engine and rose off the top of the lander. It was the first time anything had ever lifted off from the far side of the moon carrying cargo. 3 days later, at 48 minutes past 6 in the morning, the ascender found the orbiter in lunar orbit and docked with it automatically, robotically, with no one flying either vehicle. 36 minutes after that, the sample container was transferred into the return capsule. Then the mission went quiet. On the 21st of June, the service module appears to have fired its engines to leave lunar orbit. There was no announcement at the time. What we have instead is a scattering of reports from amateur optical and radio observers around the world who noticed something that looked very much like an engine burn. 4 days later, a re-entry module weighing around 300 kilograms separated and hit the top of Earth's atmosphere over the Atlantic. It did not come straight down. It skipped, bouncing off the atmosphere once to shed speed, the way a stone skips off water, before committing to the final descent. At 7 minutes past 6 in the morning on the 25th of June, a parachute opened over Siziwangbana in Inner Mongolia. Helicopters reached the capsule within minutes, 53 days, start to finish, and now the actual work could begin. 3 days later, in Beijing, there was a ceremony. Zhang Kejian, head of the Space Administration, handed the sealed container to Ding Qibiao, vice president of the Chinese Academy of Sciences. Certificates were exchanged. Photographs were taken. And then Ji Ping, the mission spokesperson, said something at the press conference that is easy to skip past. He said the samples were more viscous than previous samples, that there were clumps. He was careful about it. He called these observable characteristics, not conclusions. A man describing what he could see and declining to say what it meant. He was describing the first discovery. It just did not look like one yet. The first measurement anyone took was density, and it came back wrong. Lunar soil from the near side sits in a fairly well-understood band. Chang'e 5 soil had a bulk density of about 1.24 grams per cubic centimeter. The Apollo samples ranged from about 0.75 up to 2.29. The Chang'e 6 soil measured 0.983 grams per cubic centimeter. That is barely denser than water. Let that sit for a moment. The first material ever collected from the far side of the moon is fluffier than any lunar soil we had ever handled. Not slightly, measurably, consistently, in both the bulk density and in the true density of the individual grains. And remember, this was measured on Earth, under Earth's gravity, after being shaken through a launch and a landing. In its natural state on the lunar surface, it would have been looser still. So the obvious question is, why? The answer turns out to be about ingredients. Lower density means lighter components, and when researchers ran the mineral analysis, the ingredient list did not look like the near side at all. The soil was about 32.5% plagioclase, a pale, low-density feldspar, nearly 20% augite, 10% pigeonite, around 3.5% orthopyroxene, just under 30% amorphous glass. And olivine, a dense, heavy mineral, came in at 0.5%. Chang'e 5 soil, by comparison, ran about 4.3% olivine and about 20.7% glass. The far side sample had roughly a tenth of the olivine and considerably more glass. But the detail that mattered most was the orthopyroxene. That mineral is not typical of the local basalt at the landing site. Its presence means something arrived there from somewhere else. And that is the second finding. This soil is not local. Based on the proportion of orthopyroxene within the total pyroxene content, researchers estimated that at least 11% of the sample is foreign material debris flung in from elsewhere on the moon. Factor in the excess plagioclase, and that fraction could be higher. Analysis of the bright ejecta rays crossing the dark plane around the landing site independently suggested contamination of at least 13%, which means the container held a mixture, local ground plus wreckage thrown in from other impacts, some of them potentially reaching very deep indeed. The grains themselves are almost unimaginably fine. Researchers measured more than 72 million individual particles smaller than 1 millimeter. 95% fell between roughly 1 and 11 micrometers across, averaging about 5.5. In geological terms, that is clay to fine silt. In practical terms, it is dust, the product of billions of years of micrometeorite bombardment, slowly grinding solid rock into powder in a vacuum. Among that dust sat larger fragments. Basalt made up 30 to 40% of them. Breccia broken rock welded back together by impacts another 30 to 40. Agglutinates, grains of soil fused by impact glass, 20 to 30, and about 10% were pale fragments dominated by anorthosite and norite. There were glass beads too, small, rounded, colored black, brownish yellow, white, and green. Chemically, the local basalt was low in titanium, low in aluminium, and low in potassium. The soil showed very little uranium and thorium, far below the levels found in the potassium-rich terrain that dominates the near side. Whatever this place was, it had not been built from the same enriched material that produced the great dark seas we can see from Earth. So we had the ground truth. We knew what the far side was made of. What we did not know was what had happened to it. That question fell to a research team at the Institute of Geology and Geophysics of the Chinese Academy of Sciences, led by Professor Tianheng Shi. And their reasoning began with an insight about a single element. Potassium is what geochemists call a moderately volatile element. It does not need to be blasted apart to leave a rock. It only needs to get hot enough, and then it simply evaporates. And when it evaporates, it does not leave evenly. Potassium comes in more than one form. Potassium 3,9 is lighter. Potassium 4,1 is heavier. When molten rock boils away into a vacuum, the lighter isotope escapes more readily than the heavier one. What remains becomes progressively enriched in the heavy version, which means the potassium in a rock is a thermometer, not of today, of the worst day that rock ever had. Measure that ratio precisely enough, and you are reading a record of temperature, pressure, and material history left behind by an event that happened billions of years before there was anything alive to witness it. And here the team hit a wall. The Chang'e 6 samples were mostly dust. Finding individual grains large enough to work with was difficult, and precision potassium measurement had traditionally demanded far more material than they had. Tien later described this as the major technical challenge of the entire study, not the physics, not the modeling, but simply having enough rock. So rather than requesting more sample, they rebuilt the method. The team developed an ultra-low consumption potassium isotope protocol capable of high-precision measurement at the milligram level. In the end, they worked with 4 basalt fragments. The heaviest weighed about 19 milligrams, the lightest about 14. 4 small stones, sieved out of the soil under a binocular microscope in a clean laboratory, washed in ethanol to strip away any clinging dust, and scanned by X-ray tomography to confirm they were what they appeared to be without cutting them open. Then they were dissolved, purified, and fed into a mass spectrometer, and the result did not match anything from the near side. The Chang'e 6 basalts were isotopically heavier in potassium than every previously documented lunar basalt, heavier than Apollo, heavier than Chang'e 5, heavier than the lunar meteorites. The offset averaged about 16/100ths of a part per thousand above the Apollo baseline. The iron isotopes came out heavier too. Now, in isotope geochemistry, differences that small are not casually interpreted. They are attacked. So the team went hunting for every boring explanation they could think of. Could it be cosmic rays? Over hundreds of millions of years, radiation striking the lunar surface can alter isotope ratios through nuclear reactions. The team calculated the maximum possible contribution. Even at an exposure age of 1 billion years, an upper limit for most lunar samples, the effect landed inside their own margin of error. Could it be contamination from surrounding soil? Fine lunar dust does acquire heavy isotope signatures from space weathering, but the fragments had been ultrasonically cleaned, and the tomography scans showed no impact breccia or melt glass inside them. Could it be ordinary magma chemistry? Here the answer split in two. Modeling partial melting and fractional crystallization showed those processes could largely account for the heavy iron. But potassium behaved differently. Because of how potassium moves during melting and crystallization, those processes leave its isotope ratio essentially untouched. The magma could not have done it. Could it be the impactor itself, mixed into the mantle? The team ran the numbers for chondrites, for iron meteorites, and for Vesta-like bodies. Chondrites would have driven the isotopes lighter, not heavier, and would have left a nickel signature that simply is not there. Iron meteorites contain almost no potassium at all, and a Vesta-like impactor would have required at least 7% of its residue to survive in the lunar mantle, while pushing the iron isotopes in the wrong direction. One by one, the ordinary answers failed, which left the extraordinary one. Here is what the data suggests. The mantle beneath the South Pole Aitken basin does not merely contain heavy potassium today. It was already heavy before these basalts ever formed. The signature was not created on the way up. It was inherited from below. Something reached into the deep interior of the moon and cooked it. Numerical simulations of the South Pole Aitken impact suggest it could have raised mantle temperatures to around 2,800 Kelvin. That is comfortably hot enough to vaporize potassium. And the moon has no atmosphere to hold vapor in place. Anything that boils, leaves. The remarkable part is how little needed to escape. Under vacuum conditions, isotope separation is brutally efficient. Modeled as simple distillation, a loss of just 2% of the potassium in that region fully accounts for the signature measured in those 4 fragments. For iron, less than 2%. 2%. That is all it took to leave a fingerprint still legible 4.25 billion years later. The paper reporting this was published in the Proceedings of the National Academy of Sciences on the 12th of January. It is the first direct geochemical evidence that an impact of this scale can volatilize material deep inside a planetary body, not merely excavate it, not merely melt it, but boil it, and it carries a consequence that reaches far beyond one basin. Volatile elements are part of what makes magma. They lower melting points. They help molten rock rise, strip them out of a region of mantle, and that region becomes harder to melt and less willing to erupt. Which means the impact that dug the largest hole on the moon may also have quietly turned down the volcanism of an entire hemisphere. So the dark seas, the patches we have watched our whole lives, that every culture on Earth has drawn a face or an animal into. Their absence on the far side may not be a coincidence of geography at all. It may be the scar tissue of a single morning 4.25 billion years ago. The team is explicit that this is a proposal, not a settled fact. Their own wording is that the impact contributed, at least partially, to the observed asymmetry. The measurements are preliminary. They intend to test the conclusion against other volatile elements and to combine the results with numerical modeling to assess how far the effect reached across the whole moon. But the shape of the answer is now visible. And it lines up with something else. These samples revealed that the mantle beneath this hemisphere appears to hold less water than the mantle beneath the near side. Less water, less potassium, less of everything that helps rock melt. Almost 2 kilograms of far-side material is now sitting in laboratories in Beijing, and most of it has not been touched. Separate work has already begun tracing where each part of it came from. Researchers built a catalogue of 1,674 major source craters capable of having thrown debris onto the landing site, some drawing material from as deep as 3 kilometers. Together, those impacts appear to have delivered a layer roughly 0.5 meter thick across the sampling region. Their estimate is that the returned material is about 93% local basalt, about 6% material from the South Pole Aitken basin itself, the fraction most likely to contain genuine mantle components, and roughly 0.5% highland material from entirely outside the basin. 6%. That is the piece everyone is really after. Somewhere in that container, mixed into the dust and the glass beads and the welded fragments, there may be a few grains of the inside of the moon. The rest of the work is still ahead. The orbiter that carried the capsule home never came back to Earth after releasing its cargo it flew on, and was captured at a gravitational balance point beyond our planet, where it remains. In September of 2025, the mission team received the World Space Award from the International Astronautical Federation. Applications to study the samples have opened to Chinese institutions, and the Space Administration has said it welcomes proposals from scientists in other countries. More missions are coming to this region. Several agencies have their attention fixed on the South Pole Aitken Basin, drawn by the permanently shadowed craters near the lunar South Pole and the water ice believed to be locked inside them. But step back from all of it for a moment. For the entire history of our species, we have looked up at the same face. Every myth, every observation, every telescope, every one of the 11 sample returns before this one, all of it directed at a single hemisphere of a world that turned out to have two. We assumed we understood the moon. What we understood was the side that faces us. And when we finally reached around and took a handful from the other side, what came back was soil too light to be familiar, glass where there should have been stone, olivine that had nearly vanished, and 4 small fragments carrying the chemical memory of a day when the deep interior of the moon grew hot enough to boil. The dark seas we know so well are not a feature of the moon. They are a feature of the side that got to keep what it started with.